Okay. So many things open here. All right. Okay, so first off, can everybody online hear me? Double check again. Make sure I didn't lose anybody. And I am recording.
Yeah, just like this.
Okay. So officially, projects are due Thursday, and the idea was to talk about them, to actually see everybody's projects in class. The main motivation for me in establishing that the projects would be due on Thursday is because I didn't want it hanging over everyone's heads during break. So I had no idea if people were going home for break, what people's thoughts were, that kind of stuff. If people, I didn't want to throw it out there, so I tried to scale it in that. But if there is anyone who wants to continue working on it, wants to do sort of a prototype, wants to do a first version, a work in progress, a hypothetical prototype demonstration for Thursday, and wants to use that extra time and then kind of submit a follow-up after a week or so, that's okay. So we'll make that work. So there'll be some sort of extra time. I'd like to see, know where people are and all that by Thursday at least. I think from some people I've checked in with, it seems like things are going pretty well in general. But if you do need the extra time, hey, it's a pandemic, so no rules apply, or something like that, or whatever. We'll make all the rules flexible. So the main ideas, of course, are similar. It's to create some sort of scene, and I was thinking more about this on the way in this morning and over the weekend and sort of in general. Again, sort of, we're taking a computer graphics course, but it's graphics for games, but it's within HASS, but it's not over in CS. So how's it different from your typical graphics course? And in a lot of cases, I always come up with this kind of bottom line is that it's important to understand a lot of the theory from a broad perspective, but do I want to see you actually derive all of the equations and the math and so on? It'd be great if you could, but in the end, we're also very more concerned about how is it used? What are the end results? How would you use it? How would you use these techniques? So coming up with interesting approaches and seeing what you do with things and apply them, which means a little bit more a little bit more comfortable with finding a cool thing that you want to implement, or come up with explore different ways that things go into a scene, or so on and so on. The end kind of result. How would it be used in a game? Let's bend the rules a little bit more, right? So that goes applies to the project as well. So a little bit less strict on the derive these equations versus, hey, what was the end result? How did they get used? But obviously, to make that work, there are nuts and bolts and technical issues that we have to get over. In some cases, if we do wind up with a little bit more cutting and pasting or referring to existing boilerplate, that's kind of okay, right? So that's kind of where we are, where I'm thinking in general. So the last week or so, everything got kind of jumbled around. We left last week being a little bit more studio time, so I do have some stuff to talk about today. It's not the kind of stuff that I would expect to see in the project, but if you are feeling really excited and want to add it to the next version or something like that, I basically started with I took the Explain It Like I'm 5 version of, it wasn't quite like I'm 5. It's tough to explain anyone to OpenGL. I found a 6-year-old, and it still didn't quite work with him. But that version, I took that version and added all of this stuff yesterday. So could you do it in a day? Absolutely could. It's not meant to be, any of these techniques is sort of, let's find a tutorial, let's find some source code, let's talk through some things, and you could implement them in a couple of days. Could you write a paper and present that at SIGGRAPH on it? No, probably. But again, that's coming back to like what the purpose of this class is, to use stuff to get a feel for it, the practical nature of it, as opposed to, get published on your computer graphics innovations and breakthroughs. So this stuff I'm going to talk about, and show how it's built into what will then be, I'm going to release a new version of the sandbox that's going to have this in there. So it'll have all the ambient, diffuse, and specular lighting in it. It will have all the skybox stuff in it, and it will have a bunch of new instance stuff in. We'll talk about today a little bit as well. The only thing this version doesn't have is the object loader, which maybe I'll do another version that has my OBJ loader, but I think sounds like most people are kind of built their own, which is great, sort of stuff. But we'll probably do it. This one doesn't have that. We're just sticking with cubes for today. So, environments and shiny stuff. Sort of the hallmark of kind of modern computer graphics, or at least in terms of how modern computer graphics, most people, the first the first time they saw them and they recognized them, they got all excited about when they started seeing this environments and shiny stuff. Like the public saw Terminator 2 and The Last Starfighter. We talked, I think, a little bit about The Last Starfighter. And, of course, Terminator 2, who hasn't seen Terminator 2? It had, of course, the real shiny morphing bad guy. And The Last Starfighter, we had the shiny morphing spaceship, right? So shiny and morphing and reflective kind of stuff became kind of synonymous with modern computer graphics. No longer were they like just kind of raster or vector kind of line art and stuff like that, or they suddenly felt super real because, oh my gosh, reflections. These things look like they're in the real world, right? They're fancy, right? So we have to kind of talk about that. So in this section, we're going to study some ways to simulate basically distant surroundings and use simulated reflections, right? That's how do we put things in a scene. You'd be surprised, even if you have your current version, adding a skybox. Who doesn't immediately want to add a skybox, an environment for their scene to be in? Like if you're working in Unity or wherever, suddenly everything comes to life in 3D the moment you put a skybox around it. It's no longer just an abstract model sitting somewhere in the world. Sitting not somewhere in the world, sitting some abstract location, suddenly has some position, some relationship to the environment potentially. And of course, somehow if it can reflect the environment, be lit by the environment, or be, reflect the environment, that makes it all the more fancy and special and realistic, right? Because it seems like it's interacting with the environment. Not only is it in a place, but it is reflected by that place. How does it work? Is it really there? Is it, most of these are kind of pseudo techniques where there's a lot of, clever tricks to make it work. So we'll look at the beginning of that. We're not going to be doing ray tracing, right? This isn't ray tracing, but it does get into a little bit of, the math of if we had, we want to color something or have something reflect another pixel or another part of the environment, we will use this notion of having reflection and rays and things, but not in the ray tracing sort of sense. But it almost, immediately, if we didn't know any better, we might say, oh yeah, this must be the ray tracing part, because suddenly we're reflecting light and all that. But we're not really doing that. All right. So one of the key things that combines, while we talk about skyboxes and environments and so on, within the same group here, is because of the use of CubeMaps. Okay. And here's this section on CubeMaps in Learn OpenGL. Now, once again, I want to make sure everybody knows, but Learn OpenGL is sort of like, again, it's the textbook. It's like, feel free to read ahead and go through the tutorials there. There's also, I was looking at ogldev.com, some really fun stuff on there as well. Lots and lots of different sources. It's always tricky. Usually each one of these sites has at least one example of this, but here's the Learn OpenGL version. Here's a little text borrowed from the site, just in case you're not convinced. So what is a cube map? We talked about texture maps, right? Everyone kind of familiar with texture maps at this point, where a texture map is basically a 2D or a flat, usually square bitmap, or basically set of values that is in a two-dimensional array, right? An x and a y, and we can look up a value in there according to an x and a y position, just like a simple array, except we're kind of optimized to be pulling textures out of there. Most of the time they're four-dimensional vectors, or they have the dimensions here are red, green, blue, and alpha that we're pulling out of a 2D texture. So along comes this texture cube, though, or a cube map, which is different, of course, in that it is a texture that is sort of three-dimensional, right? Sort of three-dimensional the way that the campfire is sort of three-dimensional, if you're not familiar with that. It's an inside joke. But anyway, so a cube map is a texture that contains basically 6 individual 2D textures. So think of it as a cube, right? Each side of the cube, each surface of the cube has a texture associated with it. So there are 6 individual textures that each form one side of the cube. So in and of itself, it looked like a textured cube. So you might be wondering, well, what's the point of that? Why is that so exciting? Why am I all pumped about that? Why bother combining 6 individual textures into a single entity rather than just using 6 individual textures? And the reason is because of this pseudo 3D capability to it, right? If we were in the center of the cube at some origin, imagine, and we were to point out in any direction, we would hit the cube at some location. And the cool thing is, we're basically saying we could use that to sample each one of those, or whichever side of the cube, whichever texture we hit. So we actually, we do sample them two-dimensionally, but according to this projection of this vector starting at the origin, at the center of the cube map, right? So cube maps have the useful property that they can be indexed or sampled using a direction vector. Right. So imagine you have, like this, a 1 by 1 by 1 unit cube with the origin of the direction vector residing at the center of the cube, and you sample the texture value from the cube map with an orange direction vector that looks a bit like this, right? So we can kind of see the orange coming through in this slide, right? So if we had that vector and it poked right through the surface of the cube, voila, that's the pixel to use. So imagine the room you're in, the room we're in here, and we look around the room, the walls of the room, and we say, oh, okay, that's what the environment looks like, right? Generally, it's the walls of the room. We can kind of simplify our environment and say, all right, that's where we are. That's what we want to have in the background, right? So welcome to skyboxes, right? Skybox are the environment. It is simply instantiating a cube, right? Texture the cube with the desired surroundings according to our newfound friend, the cube map. And the fancy part is to position the cube so that it surrounds the camera. Unlike other objects where we want to see things from the outside, we want to see this cube from the inside, right? So now we have, that's why it's an environment or a skybox, or right, so on. So this is sort of what the skybox kind of looks like. The skybox texture or textured cube map, it has 6. So we have sort of the horizontal cut across the cube, and then a top and a bottom, and this is how they're kind of laid out, how OpenGL kind of thinks about them, how we're creating textures. You can create skybox textures specifically as, in one of these shapes as a single unit, or you can load them individually and tell OpenGL to go ahead and do the right thing. So this graphic is pretty straightforward. Just imagine there are the 6 sides, wrap it around, and voila, you have kind of the world as seen from the inside-outside sort of thing. But if you're inside the cube, it would make perfect sense, right? From the outside, everything should look backwards. From the inside, everything should look okay. That's the basic idea behind the skybox, right? So it's a fancy texture. It has a left, right, a top, a bottom, and a front and a back, right? So that's if we actually wanted to lay out that texture as a single texture, this is how it would be, right? Then there are kind of a few tricks, because after all, computer graphics is all about tricks. how do you make the skybox appear distant? How is it in the background? How does it not appear in front of things? What is its relationship to other objects in the scene? And it's more straightforward than you might think. First off, we're going to use a different shader. This is the first time we're going to really get into using multiple shaders within the same program. We're going to use one shader that's going to be in charge of drawing the skybox, and another shader which is going to be all our normal geometry in our scene. So the first shader and the first kind of piece of displaying the skybox, generally we're going to display the skybox first. Right? Nothing's in the scene yet. We want the sky to be in the back, so it makes sense for it to be first. And before we render that, we disable depth testing so that we don't occlude ourselves. We're basically saying, all right, we're in the middle, so whatever we see, we see. Right? Disable depth testing. Render the skybox first. So after you're done, you do re-enable depth testing when you do wind up rendering other objects into the scene so that they will draw themselves in front of whatever's in the way back. Right? And if you want to get fancy, or as your camera moves, it's going to be important that you move the skybox with the camera, right? Because if the camera moves, it's going to perceive different things in the background. So it becomes important, the view vector becomes important if you have a moving camera. Now, for now, we might just do it the simplest way. We're not going to move the camera around too much in the example here, but pretty sure the code does accommodate it, okay? Because we did that. I did that for the, okay. Anyway, all right.
Just a quick question.
Yes, sure.
Right. So if you move in the skybox and the object is outside of it, it wouldn't be drawn. But if you move the camera towards that object, it would clip into the skybox. It would look really weird.
Well, the skybox itself should never be clipped. You should always be inside the skybox, and the skybox should always be...
An object outside. As you're moving the camera, the skybox is around the camera, and you're moving towards an object that's outside of the skybox, and then it clips through.
That would happen, but one of the goals with the skybox is you should make sure that every object in your scene, the assumption would be that it would be in the skybox, right? So you'll notice in the typical shader for a skybox, it disregards things like the projection and so on because it wants it to be, drawn basically at infinite size, but from within, right? So it's different. It's not scaled and rotated the same way as a model would be, right? Generally there's no perspective or projection for the skybox. It's just way, way, way in the background. So it should never be occluded, or it should never occlude something that's in the scene, right? So that's why it should be its own path. No, it's just rendered first, right? Without a projection matrix. Right, so it's sort of, by not having a projection matrix, it's sort of like being in screen space, right? Because it has no camera, it has a camera position, but not any sort of perspective of the camera, right? Just the position. Okay. So here's a simple scene. The idea is, of course, we render from a perspective that gives us a background, and then we render everything that would be in the scene in front of that skybox, right? So in this case, we'd have the brick donut, right? Really easy to substitute different things in the background, right? But one of the things you'll notice about it is that no matter what environment we put the donut in, or the torus in at this point, the torus itself is unaffected. It's just like, boom, it's there. It's lit according to the ADS model, perhaps, if there's a light source. But it really doesn't reflect, literally. It's not lit by, it's not affected by that texture, other than it being in the scene. It's still a really cool effect, and certainly a lot of video games and a lot of things were done with this in mind, back in the day before we could do all kinds of fancy stuff. So it is still really cool, really effective. However, it does open up lots of possibilities. But before we get to those possibilities, we'll talk about some things about them. Now, if you look real close, because we are looking at cubes and things, you may notice that yes, as we're sampling, since we are, kind of sampling into corners and along these kind of creases in the world, you may notice seam artifacts. Generally, they're not all that bad because you can kind of accommodate them in the ways that you create your art to begin with, right? So if you have a skybox that actually kind of knows where the meshes, where things are going to meet and so on, it can kind of say, oh, okay, I'm actually further in the distance in the corner and things like that. So there are some artifacts if you just do a straight naive skybox because of the way that the world isn't really a cube, right? We really don't see things with corners. If you're inside a room and you did this, maybe it would look perfect, but if you're out in the world, you may occasionally notice seams if you look really, really, really closely. But the shader tries to, kind of basically, well, it doesn't try. It can come with a pretty good approximation depending on how your textures look. Right? So it works pretty well. Now, there is a way to sort of minimize that potential seaming by using a sky dome. But that's trickier, and we're not going to really get into that much. And the idea behind a sky dome, though, just to talk about it a little bit, is that it's not just a simple square anymore that we point out. Instead, we'd have a texture that is a panorama or an actual spherical panorama or semi-spherical panorama that has distortions built into it. Like you'll notice here, as you get into the sky, clouds get kind of stretched and smeary a little bit at the top of this sky dome texture. But then if you model that as an actual dome around the player, the viewer, right, that they can look at, we could potentially eliminate any potential artifacts by doing it that way, by really having a circular or spherical background. But it does require some more work because you're going to have these kind of non-uniform projections here. Like, obviously we get that stretching at the top of the sky that we'd have to somehow accommodate, whether through clever use of models or maybe instead of using a cube as the geometry, maybe you could do something like set up some kind of sphere, project that on there from inside. It's trickier, but it can do some pretty cool things, especially like imagine in this case we've got, say, the stars out around the player. Here's where it gets really interesting. You might notice, you can see the stretched stars at the top and bottom of the scene that then need to be sort of folded back in. Sometimes you can kind of make up for that in how you do the sampling, but it's not quite as neat, straightforward as a skybox, which is why, of course, we have both in a lot of game engines. Skybox is less overhead, simpler to kind of deal with. So that's the first thing. That can add a lot of life to a scene by just having a simple background that you kind of set it, forget it, put it in your game. And at the end of this, I'm taking a new approach now. I'm going to put the sample code, the useful code at the end, and I'm going to try to make sure it's the sample code that I'm pulling out of the sandbox as opposed to some of the stuff that's throughout the text and kind of a little harder to connect the dots on. So I'll show you some useful stuff at the end here to point to. But the next piece of it is, well, wouldn't it be great if in the environment it wasn't just something we looked out at, and instead, could that affect the surface of objects in the environment? And the first version, the simplest version of that, or the kind of not necessarily simplest, I mean sort of the first one to tackle, which is the primary thing is, okay, imagine you have a chrome surface, a torus that's made of chrome or a mirrored cube, something where we want to perfectly reflect what's in the environment, right? So now things move in the environment like our morphing friends in the Terminator movie and in The Last Starfighter, or the Flight of the Navigator, sorry. So now they need to look like, on those surfaces, they need to look like what is in the environment. And naively or sophisticatedly, you might say, oh, here's where ray tracing comes in. We're going to actually have all the scenes in the environment, we're going to bounce rays around, they're going to hit objects, and they're going to be rendered, so on. And absolutely right, you could do that with ray tracing, but it's very, very expensive compared to this approach. And this is pretty good for a lot of circumstances. Right? So this takes that same idea where we have imagined that the object now is seeing everything from within side of a cube map, as opposed to the camera being inside the cube map. So instead now the model, like in this case our torus here, is inside the sky map, and it needs to see what it's hitting. So therefore, we can texture our object according to what it would be, its position is in the world, but also using kind of our position so we know where the reflection is coming from. Right? So we're going to use that same environment map, but instead of just going from the origin, we're going to use the object inside to figure out the normal that points from the surface of that object. Right? This is going to be the real determining factor here. We have the surface normal, and then we have the viewer, and just like when we did our specular highlights, right? Just like specular highlighting, the view position and angle is important, or are important, to figure out, where did we get the texture here, the texel here, using this reflection according to the normal and the eye view, right? This view vector. Right. So very similar, just different calculation with regards to what the point of view is. Right? Instead of being the point of view being the center of the world, instead it's going to be the surface of a model. Right. Strategy for this, a little bit more intense. It's not just, okay, put the camera inside and render the inside of a cube. A couple more steps. First off, you have to make sure you set up your geometry. Right? So your normal, humble VAO, VBOs, you're going to need normals first off, just like we needed them for our lighting, we need them for our environment mapping. And one cool thing is if you're just going for a mirrored look, we're not going to have any texture coordinates, we're not going to have any color, we're not going to have any of that. We're just going to assume that the surface of the object is whatever it reflects. Right? So in some cases, you can even simplify your model if you know that it's just a mirror, you're just getting textures from there. As you get fancier in the sample I'll show, you can still, of course, use textures, you can use lighting, you can use, all these things can combine, but for strictly the mirrored look, you don't texture or use the color of the object and so on. That might be one of the reasons that we saw mirrored things show up first, because they were just sort of, one-trick ponies. We just reflect the surface. Don't worry about the color. Don't worry about lighting, and so on. Now, a neat thing about that, side note, right? You could imagine that instead of it being an environment, you could have a light map, right? You could say, okay, over on that wall of the room is a light, and if anything is facing that light, it should be lit up. So therefore, you can kind of see, right? This is kind of the first inkling of baking your lights, right? If you've worked in a game engine, you may have seen, you kind of set up a bunch of lights and textures and things and so on, and it takes, your game renders at 1 frame per second, and it's awful. And then you say, okay, bake the illumination. And sometimes you'll see things like light maps or baked light maps and all that. And that's where it starts to play tricks like this, where it'll say, okay, I can simulate certain things that aren't moving, that aren't casting shadows and so on by kind of baking them, hard-wiring them into the environment as textures that just sort of get mapped and and kind of corrected during that baking process. So, side note on that. We'll cover that a little bit later in some more advanced things, but that's kind of one of the things that this also enables. But for now, simple mirrored look. Okay, then in the display loop, just like our lighting, we have to make sure that we have some sort of model view matrix for the normals, right? We may need the inverse model matrix in order to correctly accommodate the way that the surface normals are transformed, because they have to move with the model, right? So we have to make sure that works. And then we have to make sure we have a textured cube map, activate it, so that we can use that as a source for all the pixels. Then the magic happens, of course, in the vertex and fragment shader. Not so much in the vertex shader. It's really just, again, similar to our ADS lighting where we're calculating the normal vectors. You just use that. But in the fragment shader, that's where it gets exciting, where we calculate a reflection we compute a reflection vector as we did for the lighting, but the output color for that is then retrieved from the cube map. The output color is retrieved from the cube map. Reflection vector is used as the texture coordinates. So this should be kind of flipped, my last two bullets. I don't know how I wind up flipping those. So that's the general idea, right? So we have an additional texture, or at least one texture that is our environment texture, which is a cube map, and you can use that in addition to other texture maps and so on. There is, I already alluded to this, major limitation of environment mapping done this way, in that because it is basically a hack, right? It doesn't really reflect the environment. It just reflects an image that's way off in the distance, sort of, right? So objects only reflect what's on the cube map. Other objects in the scene aren't reflected. There are ways around that, more sophisticated ways, where we can do things like render a scene to a texture so we know what things are in the scene, and then we can stencil those into our texture map, combining stencil buffers and the background texture and so on and so on. So there are ways to actually do this, but for now we're doing the simple thing where we're just reflecting what's on the cube map. There's another limitation which is sort of a subtle one, and it's sort of, I'm trying to come up with a good way to kind of come around it. If you're familiar with orthographic cameras and difference between an orthographic and perspective camera in terms of the way our reflections wind up. Sometimes in here we get kind of an orthographic effect where we don't get the reflection kind of scaling with the position of the object in the scene. Right? The position is okay, but there should be some scaling going on that I feel is, maybe it's just me, maybe I'm just perceiving it that way, but I'm feeling like it could be a little bit better if we somehow had that accommodated for it. Maybe it is, and maybe I'm just, my own perception is playing tricks on me. All right. So those are the two big things. Environment mapping, SkyDome or Skybox, sort of one and the same, sort of not. One is really just for projecting out there what the camera sees, the other one being what the model sees. So wanted to include some useful bits of code, and this is also a little bit of insight into sort of how I approach these things. I just go tackle once I'm sort of hooked on, say, Learn OpenGL or something like that. There's going to be certain key things in there that they'll always have that I'd hate to reinvent, like loading a cube map. Right? So here's loading a cube map. If you have your 6 different files and you don't want to dig through all of the Learn OpenGL code, this is basically what's going on. And there's different ways to do this. Right? That's the other kind of challenge all the time. Like there's always 6 ways to, I don't want to say, to 6 different ways to approach the problem at least. And this is one of them, so if you're following, this is what I did, this is the code I grabbed out of Learn OpenGL. There are plenty of other ways out there. If you follow another tutorial that looks slightly different, chances are they're just doing some things just slightly different, but the same, at the end, it should accomplish the same thing, right? So the idea here is that we are, the most important thing is that we're generating a texture, binding that texture, and specifically telling it is a GL texture cube map, right? That's kind of the most important piece. Normally we would say it'd be a texture 2D, not a texture cube map. And there are some other sorts of textures we'll get into as well. But for now, the new one is, of course, the new coolness is the texture cube map. And then we load for each of the faces here, and maybe this is a little bit more generic. I can't imagine, I don't know what would happen here if we tried to do something that was fewer than 6. Maybe 4 would work because it would read them across. Maybe that would. But it's designed around 6, but it does have this notion of saying, well, okay, maybe we have more than 6 faces or less than 6 faces. I don't know. But effectively, it loads each from each file. And the one thing, it doesn't take into account, and this is an interesting one. I never thought about this. This is not taking into account our weird, or maybe it's because I set it up earlier on. It doesn't do the STB load flipped. It's not actually in this code, but it must somehow be taken because it works. So that's the one bit, just thinking out loud. So it loads each of the faces, and if it finds data, it puts it in using GL text image 2D, and it tells it, now here's, again, a little bit more of the fanciness here. It tells it a position, a specific handle which corresponds to one of the six cardinal directions here, starting at x. So x plus 0 is x, x plus 1 winds up being the opposite, and so on, right? So we'll load each of those into texture memory, then get rid of the data that loaded from the STB as it moves along. Does a few boring things with regard to setting out, how's it mapping, how's it filtering, how's it going to wrap. And normally, if everything has wonderful, well-assigned texture coordinates, these shouldn't be too much of an issue, but that's what they're there for. And the result is a texture ID. And to show that one first, here's a bit of setting up the skybox itself. Right? So we know how to load textures now. You see this chunk down here. I shouldn't be just gesturing for people online. This part down here where it creates a vector of 6 names of files to load and turn into a cube texture here at the bottom. And the setup is actually really, really simple because it is just a cube, right? So we have the 108 floats, the 36 vertices of the cube. In this case, I just set up a VAO, a vertex array object, for the cube, one buffer for the cube. We activate the vertex array. We bind our one buffer to it. We load the positions, and that's it, right? So it's a very, very, very simple cube. The shaders are actually quite simple as well. All right. So let's take a look. Let's run some code. Let's prove that all that works. Is that running? What's going on here? Maybe it was. I got the right one here. All right, I know what I need to change here. Need this IMAT in just a minute, but for now I need to take that out. Oh. I think that crashed. Try that again. There we go. So here we have our good friend now, hopefully our good friend, the RPI spinning cube. And let's, maybe we can simplify this cube a little bit for starters here. So I'm going to set that to 0. And I'll set that to 1. Okay. So first off, the first thing we notice in here is that we have a background. The background isn't really doing much of anything. It's just sitting there doing its thing, but it is rendered first. One other thing I decided to do, which is very useful, and I'm going to suggest, well, the new version will have it if you haven't already, is I changed the order in which things are drawn so that IMGUI always draws on the front as opposed to drawing in the back. This way, if you do wind up in a jam where you know, this matrix is set really big or something like that and you can't get to it, it's a lot easier to deal with when you're drawing an object that winds up being way big and is covering the whole screen. But anyway, so in here, this is actually very similar to basically the ADS lighting example. It's using a cube. The cube has normals. In this case, the projector is really not all that subtle. The shading looks way better in person. Maybe that's a little bit better on the projector here. So this is using our good old ADS, where we had to set up a position for our fragment. We have a normal for each vertex. So we're reading a vertex array of normals. Vertex array of normals? I think that's right. Okay. Did I say that? And in the lighting piece, we can sort of ignore. So we have the ambient portion, the diffuse portion, and ultimately the specular portion down here. And we can determine how much of each we want to combine, ambient, diffuse, and specular. We multiply that by the object color, which in this case happens to be what we read from the texture up here. Right? Object color equals, and this is the normal texture, not normal like surface normal, but the standard texture, right? Our normal, our diffuse texture, yes. And if you look, depending on how we rotate here, every so often we can see the specular highlight kind of come across as we tumble like into the light. You can see the specular there as well. There it is. All right. So we have those pieces. Then, to get our environment in this portion, we have an extra step down here at the bottom. Typically, let's stop saying normally. Typically, this is sort of where we ended, where we said this part here would have given our, if you just did the typical ADS lighting, you have the ambient, diffuse, and specular piece of it, multiplying that by whatever your object color was, whether it was a standard just solid color or a texture. But now, what we do, the extra bit, is really just to say, add in some portion of the result that we just calculated according to the lighting. And you can scale this. Maybe we scale this to be, times 0.5. A little darker there. Take that out. All right, so now we see the cube in more of its just typical state here. 100% cube. Definitely looks better on my computer screen. And let's see, if I put this up to 1, we'll definitely see it. It's not 0.1, times 1. Right? All just standard cube lit with a little bit of specular. But instead, I could just say, make that 0.5 and this 0.5, which is to say half of the calculated color according to the light and half of the environment color, which is looked up in the shader. Right? The more I have, if I have that 0 and this 1, now I have a purely shiny cube. Right? You see some of them sort of tumble as they, I think this one always is just tilted enough to always just see the sky. That one comes underneath. So it's not rotating perfectly on its corner there. And let's see, let's push it a little bit into the distance. So this is the part that kind of bothers me. As I push it further, I kind of expect to see things scale a little bit better than they do. I think the problem is, let's see, is the distance at which the environment map is being sampled doesn't seem just right. But we'll see if I can improve that by the time I put out the sample code here. All right. So that's, yeah. Yes?
A little bit confused about you're sampling 3D now for the.
Sort of, yes. Yes.
Could you give some insight as to how exactly the reflection direction accurately samples in 3D for that?
Okay. So this line.
Because I see you're using a sampler cube, which is different than normal sampler 2D.
Right. So right here, this line, set of lines here, is sort of similar to our specular, if you remember, right down here, where we calculate the reflection from the direction of the light according to the normal. In here, we're basically figuring out the reflection, taking the fragment's position, the viewer's position, and reflecting that to create this new sampling point, this new vector that points at the cube, right? It's reflected. You have the view right here, fragment position minus viewer position gives us the line through according to our view, and then we have a reflection of that which puts it onto the surface of the cube. Right, that's why we use.
I get that there's the reflection vector that points to the cube. I just don't fully understand why calling the sampler on that will get you the right point.
Okay, well, it's fairly automatic. You'll notice here we're passing the sampler a vector 3. Right? Normally, when we would use a sampler, we would pass it a vector 2, which would just mean, okay, just look it up in 2 dimensions. Right? So it's doing this piece for us.
So does it like build its own 3D texture based off of the 2D that you gave it?
It does it just like this, right? I gave it 6 textures that create this set of 6, right? It creates this basically the same as skybox texture, and then it, similar to that, then it handles this part. It knows the relationship of each of those textures to the origin inside.
So it's just doing it all like behind the scenes.
Exactly. Exactly. That's what the CubeMap is there to deal with this for us.
Okay, yeah, I get it.
Okay. And this is inspired the use of CubeMaps. You can do all sorts of kind of other interesting things with them. One of the coolest ones I've seen lately a couple of years ago, if you're familiar with, I think it was Spider-Man, I forget which of the Spider-Man games on the PlayStation 4, I think, used this sort of interior mapping, which was using kind of a fancy case of environment mapping to create interiors of buildings that were fake, right? So we'd have these sort of reflected surfaces that were reprojected on surfaces of buildings as if you were looking through glass into rooms and things like that. So you can do...
Also, does the reflection back in the tube have any effect on sampling, or does that
no.
normalize it?
That just, you'll see most of the shaders just normalize that. Yeah, it has no effect on it.
Okay.
Yeah. Strictly direction, right? So once you kind of sort of master the basics of the cube map, there definitely are some fancy things you can do with it. Because you can always, like in the case of the Spider-Man interior mapping, doing things like saying, okay, well, where is the surface of the model in the world versus where is the viewer? So you wind up creating kind of interesting combinations of reflections, just recalculating your different views and normals, and you can do all sorts of odd things, like imagine reflecting on the inside of this cube instead of reflecting on the outside of the cube. That's basically what that is. I'll have to give you a link to the that one. I can point you at a paper if you want to implement your own version of interior mapping as opposed to environmental mapping. So that is sort of the basics around this. And the next thing I wanted to talk a little bit about, and this one may help shed some, I hate to say, shed some light. All of my cliches come out when I start shedding light, reflecting, normals, and so on. But this is a good one to kind of talk about, and I've hinted at this a little bit, and I wanted to kind of cover it and provide people with an example of it if they want to kind of jump in on here, which is the notion of using instances of things to kind of draw lots of stuff, right? You want to draw, say, multiple cubes, more than one cube, say 4 cubes or 5 cubes. Wouldn't it be great if you could use instancing to say, okay, I have a model of a cube, and I want to draw a bunch of those with slightly varying attributes, right? The model's the same, maybe the color's the same, maybe the texture's the same, but, simple case, I want to have them at different locations, different positions. So for that, it turns out they can be super useful in that case. Think about particle systems or some other examples I'll show in a second. Not only are they really useful for doing that, but they're also pretty darn efficient in how they do it, right? Because you're sending a whole bunch of geometry, a whole bunch of things just as a buffer to the graphics card, and the amount of context switching and changing that it needs to do is virtually none to draw potentially lots and lots and lots of things, right? So wouldn't it be great if we could just have a model and have a model transform for each instance model? That's sort of one of the basic ideas, right? You could certainly get into having different textures, different texture coordinates, or whatever you want, but the transform is one of the obvious ones. Now, one of the things you have to tackle in this case, and it's kind of a special case that's worth talking about, is this idea that, well, in OpenGL, normally we like to talk about 4x4 matrices to transform a model, and by default, I'm not sure if beyond 4.0 if this has changed, maybe some shaders, maybe some of the setup changed, but we'll just stick with 3.3 compatibility at least. OpenGL doesn't normally provide a trivial way to fill a VBO with 4x4 matrices. It likes to work in terms of vectors, vec3s, vec4, we've done those sorts of things. So it prefers vectors, but there's a way to get around that, which has sort of become commonly known, commonly endorsed. So this is I wanted to put this out there to show you if you want to use it, or if you've seen it in, I'm not sure if the Learn OpenGL version has this, or OGL Dev version has this, or there's lots of different subtle versions, but this is an important one. Imagine here, I'm going to say, well, I want to create, in this case, I'm going to create 1,000 different model matrices, right? So that means 1,000 different 4x4 matrices. And so at the top there, we have unsigned int amount, 1,000. We make room for 1,000 4x4 matrices, GLM style. And then we create 1,000 random locations between -25 and +25 in each dimension, right? So we basically have a cube with varying points, right? All we're going to deal with right now is translation. I didn't do rotation here, but changing rotation would just be as simple as adding another line there saying, okay, now add a rotation as well. But we're just going to do a translation. So we're going to have 1,000 different matrices there. Last but not least, what it does after it calculates that, it puts it into the array of them. And down here is where all the special sauce kind of is, right? So it's still a single VBO here. We're going to use a single VBO, and we're going to sort of fool OpenGL. This is all on the CPU side. The GPU side can actually handle this almost trivially, but on the CPU side, we need to kind of jump through this hoop. Whereby we're going to basically tell it we're creating sort of 4 different attributes, each one being a vec4 part of that 4x4 matrix. Right? So we set up a single array buffer, we tell it how big it is, but then we put values in basically a piece at a time there. Right? So we wind up with attribute pointers 4, 5, 6, and 7 that have the values in there. And we're telling it, we kind of mess with the stride over here so it knows how to get from one to the other. So we create this sort of interleaved, right? It's an interleaved VBO with these 4 things in there. So it tells it about that, and in the end, it kind of marries them back again. All right, so it's kind of a little bit odd, you know, even though we transfer all the data, but then we have to set this up in this sort of odd way here. So we just take that as a given. Now, that's one piece of it, the notion, how do we send a matrix 4 to our shader? But then the next part is, well, how do we make it so that we have one matrix, one transform per instance, right? So when we use GLDraw instance or GLDraw array instance, GLDraw elements instanced, we tell it how many instances of the model we want to draw. And there is a special function, GLVertex attribute divisor, which we basically tell OpenGL, say, okay, after each instance, do we want to change the value? Do you want to increment the value? If it's, so here you'll see it says 4, 1, 5, 1. That means after each instance, increment this. If we said vertex attribute divisor 4, 0, that would basically tell it, okay, after each vertex, we increment. By saying attribute divisor, this means after each instance, we increment it. You can even do things like say, oh, vertex attribute divisor 4, 2, in which case, after each pair of instances, it will increment it, right? So if you wanted things to happen in pairs or triplets or whatever, you could do that sort of thing. All right. So this is the basic idea of setting up. And the good news is, like I mentioned, on the shader side, it looks much more like a typical attribute with a type of mat4, right? So you see this part here. What location you use may vary. I'm always putting my, I wind up with 0, 1, 2, and 3 are my coordinates, my color, my texture coordinates, and my normals. So I've got those reserved, and I just say, okay, location 4 is this new instance matrix. And it's as simple as saying, okay, instead of using a model matrix here, I use my IMAT, which now uses this, instead of, say, a uniform matrix 4, which was MMAT, right? So that part is really, really simple. What could you do with this? The Learn OpenGL version has this kind of cool asteroid field. So you can change, imagine having a different orientation. You actually do, change the rotation scale and all that just by having a different transformation matrix. You can do this, right? You can scale each one differently, rotate it differently, have a different position, and so on. Or you can do crazy things like, well, how far could we push this? So this is 10,000 shiny RPI cubes at roughly 190 frames per second. Let's see if I can get it to run with the projector on here. Just to kind of prove that we can do it. So now down in here, so here's my GL draw arrays instanced, and I just had it set to 1 for now because I only wanted to draw 1. But let's draw it with 10,000. Make sure that I'm generating all 10,000. I think I left that in place. Yeah, here's my setup I matrices that I just showed you. So let's run it. All right. So here's 10,000, and it's hard to notice from inside here like this. So I like to mess with this. So you can see here's a little bit more perspective and a little bit more perspective. So that's running at about 290 plus, occasionally going over 300 frames per second for 10,000 cubes. And it's kind of cool. You can notice the reflection when it all kind of lines up. You can see, you get a cool reflection of the world there. And you can see there's a specular highlight that's going past it. So all the lighting is going on, all the reflections are going on, pretty hefty. I mean, this is I know this year's incoming freshmen will have the option of an even better laptop than this with the 3060, I think is the mobile 3060. This has a 2070 or 2060 NVIDIA, the mobile version in it. So it's no slouch, but I think it's still kind of impressive. I was doing some benchmarking over or at the end of the semester with our Viper engine that we use in game architecture and trying to get particles to work just the way that it's built without instancing it is really, really difficult to get past a few hundred cubes. And this one, well, let's prove, just to prove the point, let's make it 100,000 cubes. It's interesting, the more cubes you add, the more filled in this father cube or mother cube or parent cube winds up being. So this is still 60 frames per second, I guess. About 70 frames per second. So that's 100,000 cubes. Around 1 million, it definitely starts to get wonky. And this is without any optimizations and so on. So this is kind of crazy. So instanced objects is definitely the way to draw lots and lots of stuff. All right. And just for completeness sake, if you want to look at the normals, the cubes, the texture coordinates that I have, this is our now not so humble cube. This is the setup piece. I wanted to talk a little bit about, sort of, especially if you're comparing some of the other code that I had in some of the earlier lectures and some of the other online stuff. This notion of, you have your setup for a piece of geometry. So this is the setup for our cube here. And this is, this again, there's so many different ways to do it. This I left non-interleaved so that it was kind of obvious what buffers used what. So I had so the setup or the initialization for the cube was to make sure it has its vertex positions, it has its normals, it has texture coordinates. It does not have, what doesn't it have? It doesn't have color per vertex. So the thing I did here is, you'll see it sets up the position attribute, skips, and it kind of leaves room for the color attribute, then it has texture attributes, then has normal attributes, then goes ahead and, in this case, it sets up those instance matrices as well. And this starts to get into the notion of, it can often get to the point where you want to start using more shaders, right? Because right now, in the sandbox, this is the shader that I'm using, the vertex shader and the fragment shader. And they're going to assume that we have a vertex, a set of vertex positions, colors, texture coordinates, normals, and even that instance matrix, which is why I've been kind of having, each time I go in, I have to do a little bit of editing of my shaders to kind of make sure the demonstration works correctly. So it gets to the point where you might want to consider using multiple shaders that help define materials or textures, what's bound to what, right? So this is the ones that I'm currently using. And the nice thing is the one bit of code that I did kind of take directly and just use from or allow it to be a little bit obfuscated here. You'll see shader s.h. We'll view the code that's in shader s.h. Go to document. There we go. So Learn OpenGL has this class that they set up, a shader class. I think we talked a little bit about it earlier on, to have a version that we could kind of dynamically change because of the way that IMGUI works. But left intact everything it needed to do it, so you can just load textures from files and so on. So when you want to use different shaders, this comes in potentially really handy. And I'm using that now in here to load one texture, which is the environment mapping texture, or the one that creates the skybox, I should say. So create the skybox, and the other for the actual shading of objects in the scene. And it's not all that complex. So if we look in, I think it's in setup skybox. Setup skybox? No. Oh, no, it's right here. So inside of the main program here, in what I would say is sort of before the initialization of the skybox in the cube, is where I set up my shaders. Right? So the shader we're normally using with IMGUI is right here, and we read it in, and we allow for it to be edited and so on, which is why that piece is there. And our shader is declared earlier on as a global that we can refer to. But this is all that's involved in actually creating that cube shader. So it's just a matter of declaring another shader and telling it the vertex shader and the fragment shader for that. And then when it comes time to use that, you'll see in here in my display loop, the first piece of the display loop is what draws the background cube. All right? So it says use that cube shader that I created. It sets up, make sure that the V matrix, the projection matrix, anything it might need here, it's going to have. And bind the vertex array, the VAO that defines the cube, tells it about the textures, make sure it uses them, and it just goes ahead and draws it, kind of sets up the culling so it's from the inside and so on. So this is all kind of one chunk of display, or one render. Render the skybox. And then after that, we set up the other textures, right? So imagine that's the first chunk. The last thing it does here, important part, it says GL draw arrays to draw that skybox in the background. And then it re-enables depth testing. Then we have our textures for our normal objects in the scene, right? Which is the texture 2D, the normal surface, sorry, I keep saying normal, the regular texture and the cube texture. It activates those two and then says use the regular, our regular shader, and go ahead and do what it needs to do. Right? And ultimately, it re-enables the correct culling and still set up for potentially drawing multiple VAO-based parts of the scene, but we're just using the one right now with our 100,000 cubes. And then it draws IMGUI on top of it. Right? So there's always that notion of we have our setup here, or our init, and then we have our display, which is kind of now broken into two pieces. One which is our render our skybox, and then the second piece which is our render our objects in our scene. And I guess the third part is our render our IMGUI on top of it. Okay. Any questions on any of those things? Not so much. All right. The one thing I did, which may leave you scratching your heads, and depending on how you did it in your code, when you were working with the specular highlights and we were working with the environment mapping, you need a view position to kind of figure out where the camera is down there. And I think in most examples it probably does this. It says, oh, okay, set that up and pass that as a uniform, right? So you know the camera's position, the view position. I decided to kind of cheat here or do it a different way. I didn't want to modify, I only wanted to modify the shader and not modify my CPU code at that point. So I happen to know that I did have a view matrix that was passed in, and that the position is part of that matrix. So I wasn't doing it, the camera isn't rotated or anything at all, so I was able to just say, all right, I just grabbed the position from that view matrix, which is what this weird line is here at first, if you're ever looking through these shaders and think, well, where the heck, what is this going on? That's just pulling out the X, Y, and Z position, the translation from my view matrix, and then I just use that as my view position rather than adding yet another uniform variable, which I could, right? Graphics are all about being clever. I wouldn't say hacking. Professor Cutler would kill me if she said, oh yeah, graphics are all about hacking. That's not. It's about being clever and coming up with interesting solutions to things, unless you want to be a ray tracing purist or a PBR purist. That's why we're graphics for games. Okay, so that is it for today. So I'll leave some time for individual questions or working. I'm going to be available. Well, today I obviously have my afternoon class, so today's a little bit trickier, but I'm going to try to be as available as possible Tuesday, Wednesday as well before class on Thursday to kind of get projects together. Maybe we'll have sign-ups via Discord to figure out what order and how much time we'll set aside on Thursday. And if we do have any time, I'd like to introduce shadows, because that's cool, and it's something to think about, but again, for future stuff, right? So any questions? No questions? That aren't specific to a particular, if you're, all right. So we'll end the normal lecture part there, and we'll do the flipped classroom part now if you have any questions.